Okay, good evening again. This is Citizen Speaks. Uh, if you liked the previous videos, and especially if you like this one, please click the like button. Also, subscribe if you will. Both of these help encourage me to continue. Today, we're going to talk a little bit more about numbers. So, here we go. As mathematicians know, numbers are the essential elements of their subject, the way words are those of language. That is the reason it is so crucial to teach those who want to learn about either of these subjects the stories behind these elements and how they contributed to building the structures that make it possible to begin the quest to understand the language in which God has written the universe, as Galileo said, or the one which began with the Word. For mathematicians, number theory is the study of numbers. The previous video described some of the number systems used in mathematics. Here we shall discuss some of the unusual characteristics of those numbers. Let's start with prime numbers. Of the positive whole numbers, sorry, I'm up too fast. Um, just jumped up a little bit more than I want to hear. So the positive whole numbers, the ones which only themselves and one divide without a remainder, are the primes. They begin 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, and so on, and continue without end. The Greek mathematician Euclid provided an elegant proof that you can always find a prime number larger than your last one. For those interested, simply type Euclid and the title Elements, that's the title of his book, Book 9, Proposition 20, into your search engine. A simple formula for generating prime numbers is the following. If p is a prime number, then p equals 6 times n plus or minus 1, where n is a number larger than 3, a whole number larger than 3. That generates any prime number larger than 3. So we take, for example, 591. Subtract 1, divide 590, or add 1, and so therefore we divide 590 or 592 by 6. In either case, we arrive at a decimal number. So 591 is not prime. But 601 is, since 600 divided by 6 is 100. Notice that if you add up the digits of 591, that is 5 plus 9 plus 1, you get 15. Since 15 is divisible by 3, so is 591. Now, a little more mathematical way to write the above fact about primes is that if p equals plus or minus 1, parentheses, mod, mod 6, parentheses closed, then p is prime. This is the mathematical formula, and it involves modular arithmetic, which is a little more complicated. If you're interested, you're going to have to look that up and do a little research. It can also be generalized, this particular formula with the 6, to the following. N plus 1 is prime if n factorial is congruent to n, parentheses, mod n plus 1, parentheses closed. So that's a little, again, higher level complication and a little bit harder to figure out. You'd have to know what n factorial is, and in this case, congruent has a meaning too. A simpler formula, but still a little bit more complicated than the first one, is that if p is greater than 40, then n squared plus n plus 40 will be prime for any whole number where n is greater than 0. So those are the sort of ways of generating prime numbers. The divisibility rules for whole numbers, like the one mentioned above, are as follows. For all numbers up to 13 are as follows. Number 1, any even number is divisible by 2. 2, 3, the sum of the digits is divisible by 3. For 4, the last 2 digits of a number are divisible by 4. For 5, the last digit of a number is 5 or 0. For 6, the number has to be even and divisible by 3. For 7, subtract twice the last digit of the number from the remaining digits. For example, if you take 658, is divisible by 7 because 65, where you drop the 8, okay, and then minus 2 times 8 is 49, and 49 is a multiple of 7. So that's just the rule for 7. 8, the last 3 digits of the number are divisible by 8. 9, the sum of the digits is divisible by 9. And 10, the number ends in 0. 11 is a little more complicated. The difference of the alternating sum of the digits is a multiple of 11. For example, 2,552 is divisible by 11 because 2 minus 5 plus 5 minus 2 equals 0. 2 and 5 are the first 2 digits, 5 and 2 are the last 2 digits. So you subtract the second digit from the first, gives you a negative 3, and you subtract the fourth digit from the third, that gives you a positive 3, and negative 3 plus positive 3 equals 0. So 0, of course, is a multiple of 11 because 11 times 0 is 0. Also true for 3927, and you end up with 3 minus 9 gives you a negative 6, and 2 minus 7 gives you a negative 5, and negative 6 plus negative 5 is equal to negative 11. For 12, the number has to be divisible by 4 and 3, and 13, you take 4 times the units digit of the number, that's the last digit of a number that has multiple digits, plus the number obtained by removing the units digit of the number, and this is a multiple of 13 if it is 13. For example, 2925, you take 292, taking off the last digit, and then multiply 4 times the last digit, which is 5. So you get 292 plus 20, which is 312, and 312 equals 13 times 24. I'll put these rules up on page the beginning of the video, so you'll be able to read them. That is the beginning of the story about primes. Beginning. There's a lot more to it. Now we're going to talk a little bit about infinity. One of the most intriguing properties of the simplest set of real numbers is that they continue endlessly. That led the ancients to a numerical confrontation with infinity. They understood the connection of this property of the sets of numbers with the philosophical idea. For them, the connection between this almost tangible property and the infinity of the Almighty or the gods was unquestioned. They understood their own limitations, and those who studied numbers saw a reflection in these of the limitless universe. They only needed to gaze up at the sky on a clear summer night and see the expanse of stars to see their own insignificance, and to make the connection between the infinity the numbers implied and the one arching over them. Over the centuries, mathematicians began to clarify the different ways in which numbers reflect infinity. They found that there were different types of infinity. The simplest of these is the endless set of counting or natural numbers. They soon realized that these are associated with something called countable infinity, since any set whose elements can be assigned counting numbers is countable. Take, for example, a set of rational numbers, fractions. Since they can be written as p over q, where both p and q are integers, but q is not equal to 0, you can count them. By the way, there are positive and negative fractions, so we're not just talking about just the positive numbers. For example, 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 7, and so on. This set of fractions can be paired with the set of counting numbers. That is true for whatever you make the numerator. So you can have 2 over 1, 2 over 2, 2 over 3, 2 over 4, and so on. Again, still be countable. This also holds for sets like 1 over 1, 1 over 2, 1 over 4, 1 over 8, 1 over 16, 1 over 32, 1 over 64, 1 over 28, 128, and so on, which is just 1 over 2 to the nth. So, okay? You can show that this is true for all rational numbers. But now comes the next more intriguing discovery about infinity. There are numbers which are uncountably infinite. The set which first presents itself is the irrational numbers. For example, the square root of 2 is somewhere between 1 and 2. You begin with approximations. It is between 1.4 and 1.45, which when each one of them is squared, you get 1.96 and 2.1025. Next, you go to 1.41 and 1.43, and then you get 1.9881 and 2.0449. You continue, but you realize that you might come close, but never reach 1.414213.562 ... meaning going on forever without repeating, because of that nasty ellipsis or the dots at the end of the number. When mathematicians discovered the distinction between these two types of infinity, they also found that the countably infinite number of fractions is smaller than an uncountably infinite set of irrational numbers. As a more or less tangible way of showing this, look at the square roots of 2 above. It is an infinite, never repeating decimal, the square root of 2. Since each digit has 10 possible alternatives, one irrational number like the square root of 2 may generate 10 to the n power n possible numbers, where n is any counting number. Multiplying this infinite number by the infinite number of square roots of primes is a formidable set of infinite numbers. More importantly, they cannot be counted, since any one of them is only an approximation between countable rational numbers. There is a lot about infinity and its types, but hope it provides a little taste of the way numbers help us to understand the universe and our role in creation. These ideas help us to counter the terrifying feeling of insignificance that we face when we look at the expanse of the universe. It also helps formulate ideas, though complex, at least accessible in a way that is impossible without them. We shall continue next time with a discussion of an even stranger idea. Georg Cantor's 19th century German mathematicians, transfinite numbers, a set which consists of elements that are each infinite. So on that note, we'll end today. I hope you liked what you heard, and if you did, then please click the like button on the Citizen Speaks. And even more valuable or preferable is if you can subscribe to the Citizen Speaks, and you'll be able to access my future videos. Thank you, and good night.